All right, so we're going to continue with our discussion of completable futures today, and I'll be motivating some further reasons why completable futures exist, and in particular, describing how Java futures provide the foundation for completable futures. So we'll talk about what a future is, and hopefully that'll help motivate why they're good for a few things and deficient in some things, thereby motivating why we need to improve them to go beyond what they provide. So as we'll see, completable future implements the future interface, and then as you can see in this picture, adds a whole pile of other stuff to it. Futures have been around in Java for a long time, since about 2004, when Java 1.5 or JDK5 was released. And basically what they do is they make it possible to make an asynchronous call that doesn't block the calling thread, the caller, but instead gets a future back right away and then continues running the computation in the background. And we'll talk about how it runs in the background in just a second. A good example of something that works this way is the Executor service submit method. We haven't talked a whole lot about the Executor service in this class, but it's basically a way of being able to give work to a pool of threads to run them in the background. So executive service commit is a way of starting up an asynchronous call and returning a future. So here's just a quick snippet of this. There's something called a callable, which is a functional interface defined in Java that has a single method called call. And here we're going to go ahead and create a variable called call, just to be confusing. And we are going to assign this variable a lambda expression, which is what you see here. This is a callable lambda. And this will go ahead and create two big fractions, multiply them together, and return the result. And then down here, you can see that we go ahead and say fork join pool.common pool, so that's the common pool that we've talked about before, submit, and that goes ahead and submits this callable to be run in the future. And what submit returns is a future to a big fraction. So this is how you would submit something like that. So in the background, the processing of that multiplication of big fractions will go on asynchronously. You'll get back a future, and as we'll see in a second, you can redeem that future at some point to get its result. I'll walk through this example in more detail shortly. A future is essentially a proxy that represents the results of some asynchronous computation. So thinking back to what we just saw a second ago, we've got something running in a background, like with the fork join pool running in a fork join worker thread. It's doing some kind of computation. The client is going to get back a future when the call is made. And then if the client tries to get the result of the future, but the service thread running asynchronously hasn't finished computing it yet, it will go ahead and block. And once the service thread writes the result back to the future, that will allow the future to unblock and return the result back to the client. That's kind of the high-level view. So you can see here that getResult will suspend the calling thread until the result is available. And then when it's done, the result comes back. So this is basically the asynchronous computation, and here's where the result is obtained only after the computation completes. Now, if the client doesn't actually call getResult on the future until after the computation is completed, it'll never block. But if it were to call before the computation was completed, it would block. There's an analogy I like to use when talking about futures, which is something known as the table tent number. You've undoubtedly used these if you go to certain kinds of restaurants. They don't always come as table tents. Sometimes they come as little cards that you stick into a upright stick or post. And in any case, when you make an order, they'll give you the table tent number, and then when your order is done, they'll deliver it to you, or you can go pick it up with that number. And I think I mentioned this before, but there's a couple of different analogies here. So you have the McDonald's way of doing things where they cook the food ahead of time, put it in a heat lamp, and then they give it to you when you request it. So it's kind of serviced out of the cache, the food cache. And then they have the Wendy's approach where they give you the table tent number, And that's basically a future. You go off and do something else. You go off and talk to your friends, text your friends, read a paper, if anybody reads papers anymore. You get a drink, whatever you do, and then at some point your food is ready and they can either bring it to you or you can go pick it up at the pickup window. So that's a great example of a human known use of a future. When the asynchronous computation is done, that triggers the future and allows it to obtain the results. And so, here's the example that I just showed you, where we start off a callable running in the background while we get a future back, and then at some point, ... we'll be able to get the result of the future. So the typical way, or the way you get the result of a future in Java with Java futures, is by calling the get method. And we'll see there's a couple of variants of that, but that's the basic idea. One of the interesting consequences of futures is that the order in which you invoke calls may be different from the order in which the calls complete and give you results. So let's see if I can, see if we visualize this. There you go. So it just kind of shows you that the results may come back in a different order than you invoked them originally, which may be confusing or may not be a problem at all, but it's a consequence of using asynchronous computations. You don't always have a strict ordering in how things will finish. All right, so now that you've kind of got a high-level view of what futures are, let's talk in a bit more detail about how you program them. So this will actually walk through the example in more detail. And you can find this example, as always, in my Java GitHub account in the ex8 folder. So here's what the code looks like. We've got these big fractions, f1 and f2. And we go ahead and have a callable, which is a two-way task that returns a result via a single method with no arguments. So that's what this thing is here. We're basically initializing the callable using a lambda expression. If we were programming in the bad old days of Java before we had lambda expressions, then you'd have to do an anonymous inner class or make a separate class that is going to implement callable. But we can do it much more concisely using our wonderful friend lambda expression. Notice something interesting here. This is just a little side note so you'll understand the bigger picture. F1 and F2 are strings that are used in the context of the lambda expression. And notice that F1 and F2 are not defined as final variables. They're just good old Java variables. And so at first you might think, well, how are they going to be able to be used inside of a lambda? Don't you have to only use final things? And it turns out that Java 8 also defined a new feature called an effectively final variable. And that's described here in this article. And basically, an effectively final variable is just a good old variable that is not reassigned from the point where it's initially assigned, or initially initialized, and where it's used. So between the point where it's initialized and where it's used, if there's no other changes made to that variable, it's effectively final. So it doesn't have to actually be final, but it has to be effectively final. Later, you could reassign it as long as it's not used here before it's actually captured. That's the fancy term, captured. The submit method is the way in which you can submit a computation, in this case a callable, to an executor service implementation, in this case the fork join common pool. And that will go ahead and start the operation running in the background in a worker thread, as we've talked about many times. You get back a future from that. Then other code can run here concurrently, ... So I've obviously omitted a bunch of code, but you could have lots of code here. And at some point, we might want to get the result, which will block until the computation is done. Again, if the computation is already done, you return right away. This is a blocking call to get, which means it'll wait until the asynchronous computation finishes or some kind of exception is thrown if it doesn't finish successfully. There's also polling and timed blocking calls. So if n is 0, this is a polling call, which means it'll just check right away to see if there's any value, and if not, it'll return right away with a null. Otherwise, it'll block up to a certain amount of time. And that way you can bound the amount of time that you wait for a computation to finish. So for example, I don't know if you've ever gone to a coffee shop where, or you go to a restaurant, you order food, and they never bring your food. So eventually you probably go back over there and say, hey, you never brought me my order. And they say, oh yeah, sorry, we forgot to cook it. So you might say at that point, sorry, I don't want to wait anymore, I'm leaving. So you could leave if you decide that you're not willing to wait indefinitely to get your order. You could cancel your order as well. We'll talk about canceling later. So that's the end of the quick overview of Java futures. Any questions about what futures are? Futures are actually pretty common in a bunch of different languages. JavaScript has futures. I believe they're called promises in JavaScript. C++ 11 has a futures mechanism, and they're a very popular way to add asynchronous processing in programming languages that historically have had a synchronous feel to them, which is most programming languages.